The velocity of an object moving in an unusual way is modeled by the function v of t equals e to the power of t plus 2 over t for t strictly bigger than 0. Find the position from t1 to t equals 5 using Simpson's rule. That's the first question A. B, analytical method, and C, to compare the results that you get. Okay, let's start with A. Simpson's rule. Let's write the general form. If you have the integral from A to B, the definite integral, v of t dt, that's delta t over 3 v0 plus 4 times v1 plus v3, and these indices here are odd numbers, etc., plus 2 v2 plus v4 plus the indices here are even numbers plus vn, where n should always be an even number. So let's have a look in our case. We have the graph. Here is 1, 2, 3, 4, and 5. We want the integral from 1 to 5, right? So we have the graph of the function should behave like this. Here that is my v0, v1, v2, v3, and v4. So that's v of 1, v of 2, v of 3, v of 4, and v5. So I can write underneath equals delta t is b minus a over n. Here I have 1, 2, 3, 4 sections, so the denominator could be 4, and I want to integrate from 1 to 5, so it's going to be 5 minus 1. 4 over 4 is equal to 1. So my delta t is going to be 1 over 3 times. It's going to be v0 plus 4 v1 plus 4 v3 plus 2 v2 plus v4. That's my v1, v2, that is v4, that is v3, and v5. So it's going to be a third times we evaluate our functions at 1, so we have to find v1 is going to be e plus 2, v2 is going to be e to the power of 2 plus 1, v4 is going to be e to the power of 4 plus a half, v3 is going to be e to the power of 3 plus 2 over 5, and v5 is going to be e to the power of 5, that's 2 over 3, and e to the power of 5 plus 2 over 5. And we plug these values here for v0, v1, and so on. So it's going to be, if I do the calculations straight away, it's going to be e plus 2 plus 4e squared plus 4 plus 4e to the power of 4 plus 2 plus 2e cubed plus 4 thirds plus e to the power of 5 plus 2 over 3. This quantity inside the brackets, if you do the calculation, is going to be 443.5. It's 443.5 divided by 3 is roughly 148, and that is the area under the curve using the Simpson rule. Now if you do the analytical method, B, analytical method, so you take the integral from 1 to 5 e to the power of t plus 2 over t dt. You can split it up. So the first quantity is gonna be e to the power of t evaluated at the boundary points plus 2 ln t 1 5. So that's e to the power of 5 minus e plus 2 ln 5 minus ln 1. This is going to be equal to 0. And I have e to the power of 5 minus e plus ln 5. This can go up 5 squared. E to the power of 5 minus e plus ln of 25. And that's going to be roughly 146.67482. And let's take the difference between analytical minus numerical over analytical times 100%. That is going to be roughly 1.32513 over 146.67487 times 100%. It's going to be roughly 0.9%. So the approximation using Simpson rule could be considered satisfactory. If you take more parabolas, you get better approximation in the Simpson rule, and always the number of sections on the graph should be an even number.